Let's start lecture 11. The course is corrosion protection methods, and today's topic will continue our discussion on few more examples of better design towards protection of metals and alloy components from corrosion. Okay. So, the course is anthropic. So, more examples. Better design. So, let us talk about examples on better galvanic coupling or insulation from galvanic coupling. So, examples on designs to prevent galvanic corrosion. So, whenever we talk about galvanic corrosion, so some of the things we discussed before. So, one is as far as possible we should have same components made from the same material. So, this actually avoid galvanic corrosion, which is also called two metal corrosion, right. So, if this is, and this is basically literally impossible in some of the cases like fasteners. In case of fasteners, the fasteners must have higher strength than the materials which are being fastened. So, that means if it has a higher strength, so that means the materials will be different, material composition will be different, sometimes the microstructures will be different. So, it might have a different galvanic potential compared to the metals which are being fastened. Okay. So, if we have same material, of course, that particular situation is not arising, but it is difficult most of the cases. The second case, we should choose metals, choice of metals and alloys situating close to each other in the galvanic series. So, that would actually reduce the severity of galvanic corrosion. So, this will reduce severity of galvanic corrosion. Now, third case, let us say in the cases where we have metals and alloy components which are placed wide apart from each other in the galvanic series. So, that case definitely we would have a serious galvanic corrosion of those active component if they are connected. Okay. So, that case we must choose, we must have insulations from each other. Okay. So, that way we do not have contacts between each other and galvanic effect can be avoided to a great extent. So, third one is insulator. Okay. Use of insulator. So, rather we can put it as to avoid galvanic effect. Right. Now, let us say in some cases where insulator becomes difficult option. So, that time we should cover cathodic areas, the main theory behind is the thumb rule we have to follow, that the cathodic area should be less than the anodic area. So, that way the total dissolution of the anodic area will be much less. But in case where anodic area is small compared to the cathodic area, that time the dissolution of anodic area would be very, very severe. So, that means, so in case, so that cathodic area should be smaller than anodic area. In fact, it should be much smaller than the anodic area. So, that time this anodic part will have less corrosion. So, if we cannot ensure that, so that time we should have painting, and the paint, the thumb rule is paint cathodic area and or leave anodic area. So, if painting possibilities are there, cover everything, and if it is not possible, then at least paint the cathodic area and you can leave the anodic area. Still, that will lead to a less corrosion of anodic area, and we can have good amount of corrosion protection. Right. So, these points are to be remembered when we try to prevent galvanic corrosion. Okay. So, let us have some examples. Right. For example, if we want to have a steel, let us say we have steel component. So, let us say these are two steel component which are to be riveted, and there if we use aluminum rivet, let us say this is the aluminum rivet, this is aluminum rivet. So, this is aluminum and let us say this is steel, and we know that steel positions itself in a higher up in the galvanic series as compared to aluminum. So, there will be a galvanic coupling, and if you see the exposed area is only this much, this is the exposed area of the anode. So, that means aluminum will act as anode and this will be cathode. Okay. And we have a huge area. So, this is large area cathode, this is small area, and let us say this is exposed to open atmosphere, or let us say moist atmosphere. So, that means you have O2 as well as H2O. So, that time the cathodic reaction would happen on the cathode, and anodic reaction, which is aluminum minus 3 electron equal to Al3 plus. So, this will dissolve. So, you will see that dissolution would happen in the aluminum rivet heads, because those are the exposed area, and it will be a serious loosening effect, because this dissolution will continue there in the interface as well as here around this portion, because those portions we can have a small gap, and that small gap can create a lot of peating effect as well as crevice effect. So, this is not to be followed. So, this is bad design or the poor or bad design. So, that means one is small area large cathode, small area anode and large cathode, and the second one is we have cathodic reaction on the steel cathode and anodic reaction on the anode rivet, and the rivet loosening can happen. So, the better design would be no active metal fastener. Better to have noble anode. So, when we have noble anode for the fastener, so let us say we have these are, let us say, aluminum plates, and we can have copper rivet, okay. So, that case we are actually avoiding large cathode and small anode. So, here it will be large anode and small cathode. Here copper and this is aluminum, fine, in this particular case. But still there could be an issue. What is the issue? Because we know that the galvanic effect will be felt close to the galvanic couple. So, the galvanic effect will be felt here in this zone, and there could be undercut. So, you can see that this situation would be like this. So, you have copper and this is the aluminum. So, you can have undercut. This is copper, this is aluminum. So, this undercut is possible. So, in this case this is also not sufficient for the protection. So, in those cases I think we must use a washer. So, washer will avoid galvanic coupling between copper and aluminum. Okay. So, actually in fact this will avoid between noble fastener and active metal piece, which are to be active metal component which are to be fastened. Okay. So, this particular, this is basically the effect of insulator. So, we are actually using an insulator to have the break in the connection between copper and aluminum in this case, or we can have noble fastener and active metal component. Okay. So, for example, one such example is, so here we can use, instead of washer we can use some sort of, so this is a insulator. So, this insulator could be a small polymer which will avoid that connection between the aluminum and copper, fine. So, that is the possibility. So, that means this is still, this is bad, this is not better, not fully covered, from galvanic corrosion. So, this is fully covered. I can say better design, or not this. So, this is the effect. So, this is the effect, fine. So, this is the effect that undercut. Okay. So, I can say that this is not good at all, but we can have like this. Let us say this is my let us say this is noble fastener. This is active metal component. So, what I will do, I will put a small insulating stuff here, as well as I will try to block this portion. These portions are blocked, the small gaps are blocked. Okay. So, that way I won't allow any fluid to ingress between the small narrow gap between two metal components, as well as I am having insulator between noble fastener and active metal component. So, one such example we can have a drawing. Let us say a flange joint. So, what we will have? So, the flange joint part is like this. The opposing surface is this. Okay. So, this is a joint there. So, let us say we have to avoid that contact between these two opposing ends. We can use our insulating gasket between these two. So, we can have an insulating gasket. Okay. So, this is my insulating gasket, which can be made by glass reinforced epoxy. Okay. So, this is called GRE. What happens? This actually prevents the connection between opposing ends of that particular flange joint. Now, there could be possibility of corrosion of the bolts. So, there also we should be careful in having insulation. So, let us say here we have a bolt, and then so this is the design, this is the bolt, and we can have a washer you can have a washer here. And on the other hand also same design. And let's say this is my screw threads. So we have screw here, we have screw here. So this particular part will enter through this, and then from both ends you fasten it. But here also you can have a washer. You can have a washer here. So this washer will, so this is also washer. So that means you are preventing the connection between all those metal components where you can experience galvanic corrosion. Okay. So this is effect of insulation. Fine. Now coming to this is flange welding, sorry, flange joint. Okay. Now some more examples on this area factor. Let's see if I weld. Let's say this is my parts and I am welding. So welding, we should do the welding like this. Let's say this is welded. Let's say this is my weld part. And couple of design aspects. One is this top part should be grounded. Then things will become like this. Right? And this is the modification. And now here this is the part which is to be welded. So this part here we have to make sure that this should be noble weld material and this will be active. If it is same, that's better, but if we don't find the same thing, then it should be active, so that here also large anode, small cathode. So the corrosion effect of the active component would be less. And when you grind it, so that means when you try to fix it in a component, that time that there will be matching surfaces. So there will not be any much of play between the two adjoining surfaces. Let us say this surface, this particular surface you are trying to match with another surface. If we have a little hump over it, then definitely it will lead to a mismatched surface. Okay. So that's why the grinding would make it better. Now, so now the point is, let's say we have joined by welding and the weld material is noble, whereas the parts which are welded, those are active to that particular noble material, the weld part, which follows this large anode and small cathode as per our theory, thumb rule. But let us say we have a situation, the same situation, let us say we have on top of it or strong corrosive. If this is the case, like on top of this surface we have small corrosive. If it is a small corrosive, then if you see around this part, locally locally around this zone, we have a strong galvanic effect because it's a strong corrosive. So, the surrounding around that part where the connection between active and noble components are setting up. So, there will be serious corrosion aspect. So, there could be undercut also. Around that zone, you can have pitting. Pitting corrosion could be a possibility. So, in that case, if we foresee that strong corrosive will be experienced on the surface of the welded part, it is better that if the strong corrosive is there. So, the better that the design modification would be, we reverse this. So, instead of this, we put this. So, now the modification would be like this. So, if you see now the contact between strong corrosive and the weld part is at the point, almost at the point, okay, a very small tiny area, and then the effect of galvanic corrosion just at the junction of that tiny area of that noble component as well as the active surrounding will be much less compared to this. If you compare these two, so this will have high degree of local corrosion around weld in the active component. But if you compare this, so it will be much less. Okay. So, this is my separation. Okay. So, here it will be having much less effect compared to the other one. So, this is one more example. Now, if we have another, let us say another let us take another example. Let us say we have a component, on top of it if we have a coating, let us say this is my coating area, and this coating is cathodic to the metal on top of which coating is done. So, now if that coating is intact, there is no scratch, that means there is no exposure of the underlying metal, then there is no issue. But if by chance there is a scratch on top of that coating, and if the metal underneath is exposed to the corrosive, then there will be severe galvanic corrosion around that scratched area. And in fact, that scratched area will be protected, but around that particular scratch area will have lot of corrosion. Okay. So, if we let us say try to look at the local zone. So, let us say this is my exposed area. So, this is the exposed metal, and rest of the part cathode. So, this is large area, here also large area, and this particular part small anode, fine. Now, this particular area will be undergoing corrosion. So, cathodic reaction, let us say if it is in moist environment, so then this reaction would happen. And here let us say if it is iron, this would corrode. So, this is a typical example if we have tin coating on iron or steel, okay, and let us say carbon steel which has no passivation tendency, right. So, this is another part. So, that means if we experience scratchability, so it is better to have a coating which has barrier protection, that means it can withstand erosion or wear, as well as it should be anodic to the underlying surface. So, that means it is just like a galvanization where zinc coating is placed on top of iron. Okay. So, iron is protected due to the sacrificial effect of zinc when there is a scratch on that zinc coating and exposure of the underlying metal to the environment, right. So, that is the solution. So, it is a better to use okay. So, that is the solution. So, let us give one more example on cathodic and anodic area, and this is related to coating. Okay. So, this was example on large cathode and small anode. So, let us have example on coating the cathode. So, let us say if you have a container, let us say this is my container and you have an electrolyte here, let us say salt water or acid, let us say. So, if you have some anodic material inside it, so let us say this is anodic material. Now, that anodic material, if it is a starer kind of stuff, so that if somebody is thinking that this is anodic, this is active metal, so there could be possibility of high degree of corrosion. So, let us paint it. So, if somebody can paint it, so the painting is done. So, this is the painting part and the painting part is everywhere. So, let us say this is a phenolic paint. So, this blue color is the paint part. And let us say this is organic pen. And this is noble metal compared to the center part. This is active. Okay. Now, interesting part is whenever we have, let us say, organic paint, and by any chance there is a small peel off in that particular paint. Let us say we have this paint So, this is the paint part, a small segment is out. So, this is the out part, no paint. And now we will experience severe galvanic corrosion in this zone. So, this is my that metal component, the active metal component. Here we will have good degree of corrosion locally, and this will happen locally. So, the local degradation. Okay. Now, since a small area is exposed to the solution and the solution interface is this, let us say solution is here. Okay. So, now this small area is exposed. So, and this is active metal compared to the container metal. So, then and this is electrolyte and salt water or acid, it is a highly conducting electrolyte and highly corrosive also. So, then you have a large cathode. So, this entire internal surface acting like cathode, large cathode, and this will be small amount, small anode. And again the effect of large cathode and small anode will be felt in the local region of that anode material. So, this is bad. So, the better design would be same thing, this is the tank and this is the central component. Okay. This is the tank. It is better to coat the inner surface of the active component, noble component or the cathode, because as per galvanic series in the same solution, the container metal is sitting above the central metal part, which is the anode. This is anode and this is cathode. But since we have painted the entire inner surface of the container, so that means we have covered the entire cathodic area with a non-conducting paint. Now, even if there is a small peel off in that paint and the anode area we are exposing, we are no paint. So, even there is a small part which is exposed, let us say this part is exposed, a small component which is exposed. So, here also if you see, this is a small cathode and here we have a very large anode. So, that means we have a very little effect of corrosion on the large anode. Corrosion would be there, but it will be much lesser than in the previous instance. So, this is better design. Better design. And the thumb rule is always coat the cathode and you can leave the anode material uncoated. Okay. So, we have discussed some of the examples related to galvanic corrosion and better design to protect materials from galvanic corrosion. So, we will discuss few more examples in our next lecture. Till then, thank you.